Hello students and welcome back to this channel. So in this video we're going to be handling the final video under electrochemistry. So this video is going to be suitable for students in senior 6 together with those ones that are in for their new curriculum as nothing changed about this topic. So this video is presented to you by Olgembe Yusuf and you advise subscribe to the channel. Share the video to your friends so that you can all benefit together. So now with the previous video, we are looking at electrode potentials together with the standard electrode potentials. And then we looked at how we can perform experiments in determining the standard electrode potentials of the different metal elements or metal ions using 1 molar concentration of their solution together with them as elements. But here, under this experiment, we saw that we are using standard hydrogen electrodes as our main electrode in determining the electromotive force or the EMF that is produced by the other cell, which in turn gives us the standard electrode potential. So in this video, we are going to be specifically looking at electrochemical cells, and in these electrochemical cells, these ones are highly examined, and it's very hard to find a paper 1 of chemistry in 2 consecutive years without studying this topic. So you're going to be looking at it in details, and you're going to start by saying an electrochemical cell is going to be that cell that is going to convert chemical energy into electricity, and the examples under that is going to be the Daniel cell, together with the dry cells that you use at home, together with the batteries that you see in your parents' cars. Now proceeding, we're going to say that the cell is going to consist of 2 things. It's going to consist of the metal together with the metal ion. But these ones are going to be in terms of conversion of cells, and you're going to look at what that means. So the metal or metal ion is going to be called a conversion cell. It is either going to be called the right-hand electrode, or it is going to be called the left-hand electrode, and you're going to look at in details how we can identify each of them without any confusion. So proceeding, we are going to say that when a metal or a metal rod is dipped in 1 molar solution of its ion, the cell generated is going to be called the half cell, just like we looked at it in the previous video. Then proceeding, we are going to say that a magnesium half cell is going to be therefore made by dipping a pure rod of magnesium in 1 molar solution containing its ions, which are the magnesium ions. For example, 1 molar magnesium sulfate solution. At standard conditions, when we set standard conditions, it must be at 288 Kelvin together with 1 atmosphere. So with that, what is going to happen is that the magnesium ions in the solution are going to be discharged onto the rod to form the magnesium atoms. And this cell here, what you're seeing here, let me first explain this in details before I proceed. When you see anything like this, we read it as either oxidation or reduction, and we read it going to the right hand side. So here you can see that the oxidation state of magnesium changed from +2 and then it went to 0 after being discharged. So that means that this half cell is a reduction half cell because there was a decrease in the oxidation state from +2 to 0. So that's a quick recap about that. But we're going to look at that further in details as we proceed. Now, considering a silver half cell, it's going to be made also by dipping a silver rod into 1 molar solution of silver ions, such as silver nitrate solution, 1 molar. And when you do that, the silver ions present in that solution are going to be deposited as atoms onto the rod of silver. And also this is a reduction of cell equation because oxidation state is changing from +1 to 0. And therefore, you're going to proceed by saying that the reduction equations, together with the reduction potentials for the half cell equations, are going to be represented by the following. So you saw that we have a reduction in the oxidation states across the half cell equations we wrote. So to write that in terms of an equation, it's the same as to reduce the oxidation state of any cation. you add electrons to get an oxidation state of 0. So since it involves reduction in the oxidation state, since this equation is involving reduction in oxidation state, it's called a reduction potential or a reduction equation, together with the second equation of silver. So we're going to say that here, the relative values of these voltages shown of magnesium ions are going to be more difficult to reduce as compared to silver ions. So silver ions are going to easily accept electrons from magnesium in the half cell equation to lose, and also magnesium is going to lose electrons to the silver ions in the half cell equation. Now we are going to look at this in details. Here it was not well elaborated under the calculations. So we're going to proceed by saying that, therefore, by conversion, the electrode with a more negative standard electrode potential is going to contribute to your left-hand electrode. Now let's understand this one properly. We are having what we can describe this in terms of negatives, or we can describe it in terms of negatives and positives, or we can describe it in terms of the one which is positive. Now what you should understand here, your left-hand electrode is going to be the one which is more negative. In other words, it's going to be the one which has a less value. So the left-hand electrode always has a less value. So left-hand electrode has a less value. And then your right-hand electrode is going to have a high value. So having noted down that, so here we are saying that according to these values here, you are saying that the one which is less is going to be our left-hand electrode, and our left-hand electrode here is going to be that of magnesium, simply because its standard electrode potential is negative 2.38. So it's more negative as compared to positive 0.80 of silver. So the one which is more negative constitutes the left-hand electrode, and the one which is less negative or which is more positive is going to be the right-hand electrode. Your aim is to note the one which is less. The one which has a less value or which has a more negative value becomes your left-hand electrode. This is very important in terms of calculations because this is going to be everywhere. So if at all we have been given all values in terms of negatives, the more negative electrode potential constitutes the left-hand electrode, and the less negative is going to contribute the right-hand electrode. If you are given a negative value together with a positive value, just like in this example above, that means that the more negative, which is going to be for magnesium, is going to constitute the left-hand electrode, and then the more positive is going to contribute the right-hand electrode. If at all we have been given values and they are all positive, you make sure that the one which has the less value must be the left-hand electrode, and the one which has a higher value must be the right-hand electrode. So we are going to look at that more in more details under the examples which I gave later on. So with that, let's look at what we call the cell notation or the cell conversion. Now cell notation or cell conversion by definition is going to be the symbolic representation of an electrochemical cell. So symbolic representation of an electrochemical cell is what we call the cell notation. Sometimes this definition is asked in mocks. So it's simply a symbolic representation of an electrochemical cell of any electrolyte. So here we are going to look at the steps that are going to be involved for us to write a cell notation. Now, just like I said, here in these equations, your aim is to look at whether we have two types of potentials. We are going to have what we call reduction potentials. We also have oxidation potentials. Reduction potentials is where the element present on your left-hand side has a high oxidation state as compared to the one which is present on the right-hand side. In other words, if you are to draw an arrow from here to here, you see that oxidation state is changing from +2 to 0. So that we call that one a reduction potential. And its value, this value here, is going to be called the reduction potential value, though it's also called the EMF. Also here you are seeing that silver is reducing from oxidation state of +1 to 0, which also involves a reduction in the oxidation states, which also qualifies to give us a reduction potential. So you're going to take some of the notes here, and you're going to say that make sure that the given electrode potentials are reduction potentials. In other words, you make sure that the oxidation states are decreasing as you are going to your right hand side. If at all the equations are altered, we are going to look at that, and you're going to see how you can that. But make sure that you notify reduction potentials. Reduction potential equations are going to be those ones where this equation or the half cell is going to proceed with a decrease in oxidation state. These ones were good examples. You are seeing that for that of zinc, the oxidation state turned from +2 to 0, and that of silver, oxidation state turned from +1 to 0. And that's what we call a reduction equation or reduction potential. So here we are going to say that instead, if at all you are given oxidation potentials, we reverse the reactions. And after doing that, we also reverse the sign present on the electrode potentials. So for example, in other words, for example, if you're having the following equations, the electrode potentials given, we say that the electrode potentials given above are going to be reduction potentials simply because you are seeing a reduction in the oxidation states. So if you look at these equations, under these equations, you are seeing that this equation is proceeding with an increase in oxidation state. And if that's the case, if at all we are having an equation proceeding with an increase in the oxidation state, it does not become a reduction potential, but rather it becomes an oxidation potential because it's proceeding with an increase in the charge. So what you do is that we reverse these equations, but as we are reversing them, also the sign that is present on the EMF changes. So you're going to reverse what is present on the right hand side is going to be shifted to the left, and what is present on the left is going to come on the right hand side. And after reversing them, we change the sign which is present on your EMF of that cell. Together here, if you look at the second equation, also here, if you recognize oxidation state here, we have -1, and on your right hand side you're having 0, and 0 is greater than -1. That means that for us to make this one, to change it from an oxidation potential to reduction potential, which we want under calculations, we have to reverse this equation. But as we reverse the equation, we have to also change the sign that is present on the EMF of that cell. So what we are going to do here is that we are going to say that the reduction potentials given above are going to be oxidation potentials for the reason that I've just explained. So we are going to reverse them, but as we are reversing them, we also reverse the signs that are present on their EMFs. So that being said, we are going to reverse, when we reverse the equations, you will notice that electrons are going to come on your left hand side, and that's how you recognize a reduction equation. And also the oxidation state are going to be coming from +4 to +2. That means that this one becomes a reduction potential. And after doing that, we also change the sign that is present on their EMF. So initially they were negative, so we have made them positive, and the same applies to the second equation. Now we are going to make some of the following areas, or we are going to highlight some of the following. You are going to always use a mimic of ionic, this meaning that oxidation refers to the loss of electrons, and therefore they must be on the right hand side. But reduction is the gain of electrons, and therefore they must be on your left hand side. It's as simple as that. Or you can use this one, but you pick the one that you are most conversant with. So proceeding, we're going to say that in some cases, one electrode potential can be given as a reduction potential, and the other one may be given as oxidation potential. So in such a case, only one equation is going to be reversed, and these ones are very common in papers. Before doing any calculations involving electrochemical cells, you need to first make sure that all the equations you are having are reduction potentials, or they are reduction equations, simply by looking at the oxidation states. The oxidation state must be decreasing as you move from your left hand side to your right hand side. That's how you recognize that this one is going to be a reduction potential, or it's going to be a reduction equation. And if it's not the case, you make sure that you reverse such an equation, and you also reverse or change the sign that is present on its EMF of that particular cell. So with that being said, we are going to first look at some of the steps that you can look at when you're writing equations together with the cell notation. So we have looked at how we can identify oxidation equations or oxidation potentials together with the reduction equations or reduction potentials. Now we are going to go to step 2, and here we are going to say that then you are going to write down the equation that is going to take place at the anode. Now the anode is going to be your negative electrode, and also the equation that is going to take place at the cathode. The cathode is going to be your positive electrode. Now here, the equation at the anode should be oxidation, gain of electrons, and at the cathode it should be reduction. Now just to make a brief explanation about that, is that the anode is responsible for oxidation reactions, and the cathode is only responsible for reduction equations. That means that at the anode, I need you to write oxidation equations. That means that from your left-hand side to your right-hand side, I need to see, I'll be looking at oxidation states, and I'll be seeing whether the elements you are having are changing from oxidation state. The ones that are present on your left-hand side must be having a lower oxidation state as those ones that are present on your right-hand side. In other words, your forward reaction must proceed with an increase in the oxidation state, simply because the anode is a site or is an electrode for oxidation, and we define oxidation simply here in electrochemistry by an increase in oxidation state of a particular ion or a particular element. Now at the cathode is going to be the opposite. The cathode is where reduction takes place, and we have looked at the reduction equations. That means that in the cathode I need to see an equation like this one up here. I want to see reduction taking place, that this tin which is having +4 oxidation state later formed the +2 oxidation state, because at the cathode is where we have our reduction equations taking place, or loss of electrons. So now we are going to be considering these equations. If you look at equation number 1, it's going to be a reduction equation, because, and this is going to be the equation at the cathode, because you are seeing reduction taking place. Tin is coming from an oxidation state of +4 and it's going to an oxidation state of +2. So that one qualifies to be a reduction equation, simply because there's a reduction in the oxidation state, and the same applies to this equation. So both of these equations, since they proceed with a decrease in the oxidation state, they qualify to be reduction equations, and reduction takes place at the cathode. So these are the equations that take place at the cathode. Now proceeding, we have to identify which one is going to be our left-hand electrode and which one is going to be our right-hand electrode. I told you the left-hand electrode has to be less as compared to the right-hand electrode. So since the left-hand electrode is less as compared to the right-hand electrode, if you compare positive 0.15 and positive 1.07, the less value is positive 0.15, and this one qualifies to be our left-hand electrode. Now the left-hand electrode is also called the anode, and the one which has the highest value qualifies to be our cathode, or the right-hand electrode. So here we are going to say that after identifying your anode and after identifying your cathode, you have to write equations that are taking place on each of them, and you write them appropriately. So the anode, we want an oxidation equation. That's why we are going to reverse this equation to give us an oxidation equation or an oxidation reaction equation, simply because at the anode, oxidation takes place. But quote me right here, if you are doing calculations, we need reduction equations. But if you are being told to write an equation at any particular electrode, you must write in respect to what that electrode does. So at the anode, we have oxidation. So it means that we need to write an equation of reaction in terms of oxidation, tin increasing its oxidation state from +2 going to +4. But at the cathode, reduction takes place. That means that we leave the reduction equation as it is, because that's what takes place at the cathode, or the right-hand electrode. I hope that has been very clear. We say that how do you identify your left-hand electrode or the anode is it must have the least value, and then the cathode must have the greatest or the higher value, and it's going to be your right-hand electrode. Now let's first discuss some of the very important issues when you're writing cell notations or cell conversions. So one, and you should note these ones very clearly because these ones are the principles that we base on when you're marking the cell notations that you present in your examinations. So one, you're going to be using a vertical line to separate different phases. When I mean different phases, I'm meaning aqueous from a solid, or a solid from aqueous, or a solid from liquid, or aqueous from gas, or solid from gas, for as long as the two states are of different states. However, if you're having the two states existing in the same state, for example, liquid and aqueous, these ones are of the same phase, they are all solutions, or they are all liquids in nature. So we separate these ones. These ones cannot be separated by a line, but we separate them using a comma. For example, if you look at Roman number 2, I've told you that if you're having similar phases, for example, things that exist as solid, we use a comma to separate such elements or compounds. And also aqueous and liquid, because all these ones are going to be solutions. So since they exist in liquid state, we also separate them with commas. We only use a straight vertical line when you're having two different states, a solid and a liquid. That's when we use commas, or a solid and a gas, or a liquid and a gas. That's when you're going to use a straight vertical line. But when you're having things existing in the same state, such as solid and solid, and also aqueous and liquid, we are going to be using commas. Now, when we are going to be using the vertical line, now this vertical line is going to represent a salt bridge. Remember, the function of the salt bridge is to connect cells internally and allow exchange of ions without mixing the two solutions in the half cells. So the double vertical line represents the salt bridge. However, if you use the polar spot, we shall represent that by a vertical line which is dotted. But mostly you're going to be using two double lines to indicate that you have separated the two cells. So these two vertical lines indicate separation of the two half cells that you're having by a salt bridge. Now, since you have already identified how you can identify your left-hand electrode, which is going to be the anode, and also your right-hand electrode, which is going to be the cathode, that means that when you're writing your cell notation, the equation at the anode should be on your left-hand side, and also the equation for the cathode should be on your right-hand side, in respect to what each of them represents, because at the anode, we have oxidation. For example, if you come here down, and you look at this reaction, you are seeing that here tin is increasing its oxidation state from +2 to +4, and then we separate the two using a comma because they are present in the same states. So since this is the left-hand electrode, which is the anode, the way you are writing your ions must be in terms of oxidation, because that's what takes place at the anode, and the anode is on the left-hand side. But on the right-hand side, we have what we call reduction, or the cathode cell. So we need, whichever you're writing, you must represent it in terms of reduction. So here you're saying bromine from oxidation state of 0 to -1, which implies reduction. And this is the reaction that is taking place at the cathode. We separate the two components using a comma because liquid and aqueous are the same, exist in the same liquid state. So that means that we don't have to use a straight vertical line, but rather we use a comma. We say the comma is going to separate similar states. Now you're going to notice that you're putting platinum on both sides because you have told you that for cells that are not going to contain any solid metal electrodes, we are going to use an inert electrode such as platinum on each side. For example, here you're having aqueous and aqueous, we don't have any electrode, so we assume that we don't have where an electrode, a solid electrode, where our reactions are going to take place. So we introduce an inert electrode, which is platinum, and we put it on that half cell. Here also we didn't have any solid electrode. That's why we also placed platinum at the end. But if at all you had a solid component, platinum does not qualify to be positioned at such a position. Now with all those steps, you are now fully able to write a cell notation. So you are saying that here, the cell notation, if well written, is going to guide you on even how to draw a label diagram of an electrochemical cell, although we are not going to examine this. So we are going to look at the more examples that were given under this section. So number one, you are provided with the standard electrode potentials of 12 cells. Now here you should first recognize, are you given reduction potentials or you are given oxidation potentials? According to these ones, I'm seeing that oxidation states are decreasing as you are going to our right hand side. That means that both of these ones are reduction potentials. And if they are reduction potentials, you are free to calculate. Now they are telling you to write the equation that takes place at the cathode. First of all, you should know what takes place at the cathode. A cathode is a site for reduction. That means that you should write a reduction equation. But also you should identify which one is going to be your cathode, or which one is the cathode is a right-hand electrode, and then the anode is the left-hand electrode. And then we say that we identify those two by looking at the electrode potentials. The one which has a very less electrode potential becomes the anode, and the one which has a higher electrode potential becomes the cathode. And the anode is always on the left-hand side. The cathode is always on the right-hand side. So here, if you identify this one is the least one here. Since they are all reduction potentials, you must first make sure that they are all reduction potentials. That's the first thing. After you identify which one is the anode and which one is the cathode. So this one is having the least value is going to be our left-hand electrode or the anode. And this one is going to be our right-hand electrode or the cathode. So equation at the cathode must be a reduction equation, and it's going to be exactly this one. Equation at the anode must be, which anode is your left-hand electrode, which is the first one. So equation at the anode must be an oxidation equation, because at the anode we have oxidation taking place. So we shall reverse that reduction equation to get an oxidation equation. Then the overall equation for the reaction. This is very important. We get overall equation for the reaction just like the way we did in redox reactions, simply by adding the two equations, but we eliminate electrons. Now part B, you are going to write the cell notations according to what you have written above in part A, Roman number 1 and Roman number 2. So with what has been explained, at the cathode we have reduction. So this equation, we must write an equation that shows reduction. Oxidation state is changing from +1 to 0. So this qualifies to be the equation at the cathode because it's a reduction equation. But at the anode we have oxidation. So we need to reverse our equation so that we get an oxidation equation, which shows that the oxidation state of magnesium is increasing from 0 to +2. So this qualifies to be an oxidation reaction, which is the purpose of the anode. Then you have said that to get the overall equation, you add the two electrons by eliminating, you add the two equations by eliminating electrons, and you do that just like the way we did in redox reactions. So you have to multiply the first equation by 2. After multiplying it by 2, you cross out electrons, and then you're going to end up with the overall equation to be the following. I hope that is very simple to understand. You get your overall equation by eliminating electrons, just like the way you did it in redox reactions. Now for you to write a cell notation, just like we said, if you're having a solid electrode, there is no need for you to write the platinum on either side. Then like here we had solid electrodes, so that means that there was no need for us to put platinum on either sides. So this side, on the left hand side, we say that left hand side is owned by the anode, so whatever you're writing must be in terms of oxidation. But the right hand side, we say that it's going to be owned by the cathode, so whatever you're writing must be in terms of reduction. That's why in this cell notation you're saying that magnesium turned into magnesium 2 ions, because we made this is an oxidation reaction. It is showing you that magnesium was oxidized to get a +2 oxidation state from 0 to +2. But on the right-hand electrode, which is the cathode, reduction took place, whereby silver reduces oxidation state from +1 to 0. So that's how we write cell notations. On the left-hand electrode, it must be the anode reactions, and the anode reactions involve oxidation. But the right-hand electrode must be cathode reactions, and cathode reactions involve reduction. Now we are given these equations too. If you analyze these equations, I'm seeing oxidation state is changing from +2 to 0. That means that this is a reduction equation. Also, this one is from +2 to 0. This is also a reduction equation. That's the first step. After analyzing that, after making sure that you have the two reduction equations, you make sure that you analyze which one is the left-hand electrode or the anode and which one is the right-hand electrode or the cathode. The one which is the left-hand electrode is the one with the least value. So that means that zinc is going to be your left-hand electrode, and the other one automatically becomes your right-hand electrode or the cathode. The left-hand electrode is going to be the anode. Right-hand electrode is going to be the cathode. So you're going to be writing the reaction at the negative electrode or the anode, and also the reaction at the positive electrode or the cathode. After that, you write the overall equation for the reaction, which I will say that we do that by eliminating electrons. Then later, we write the cell notation for the Daniell cell. Now, since this one does not vary from the example that you have just elaborated, I'll just display the solutions, and then you refer to the example that we did earlier on. Now let's put emphasis on this question, which may seem to be quite tricky for you people. Now here you need to understand what is happening. Here I'm seeing that tin is increasing its oxidation state from 0 to +2. That means that this one is an oxidation potential. And I say that we don't want oxidation potentials in the first place. So the first place is for you to convert oxidation potentials into reduction potentials. So we are going to start by reversing this. And this value of EMF is going to change to negative 0.14. If you look at this one, I'm seeing also manganese is increasing its oxidation state from +2 to give a compound which is present in the oxidation state of +7. This is read as acidified manganese 7. So also this one is an oxidation potential. That means that for us to start anything on this question, we have to start by reversing these electro EMF values and reversing these equations to get reduction potentials. After getting reduction potentials or reduction equations, then we can proceed and we identify which one is our left-hand electrode or the anode and which one is our right-hand electrode or the cathode. After that, you write the equation for the overall reaction and later we write the cell notation. So let's do that quickly. Let's start by reversing to get the reduction potentials. Now converting the given values or the given information into reduction potentials. Now here, after converting, you will see that tin is having its oxidation state decreasing from +2 to 0. So that means that this qualifies to be my reduction potential. Also manganese, its oxidation state here is +7. So it is being turned into +2. Now this also means that this is going to be our reduction potential. Now I look at which one is the less. The less value constitutes the left-hand electrode or the anode. So tin is going to be my anode, and then the other one automatically becomes my cathode or the right-hand electrode. At the anode we have oxidation, at the cathode we have reduction. That's what you should have in your mind. So at the anode, when I'm writing the equation, I make sure that it's in terms of an oxidation equation. So here you see that the equation that is happening at the anode, tin is increasing its oxidation state from 0 to +2. Now this qualifies to carry a full mark because it's an oxidation reaction. By the cathode, we have reduction, so you have to write a half cell of the reduction. We did this in redox reactions. So you write a half cell of manganese, acidified manganese 7 ions in solution. So they are going to be reduced to give manganese 2 ions together with water, and then you write it well balanced. We looked at balancing of these equations under this topic, under transition elements, and I explained them in details. Now for you to get the overall equation, we say that we use the redox knowledge, whereby you eliminate the electrons. So you have to put here 5 and you multiply this equation by 2. After that, you add the two equations by eliminating electrons, and you're going to end up with the overall equation to be this. Now for you to write your cell notation, simply you make sure that on the left hand side of this double line, you are having an oxidation equation. So here tin is oxidized to tin 2 because this is the left hand electrode. we must see oxidation taking place in your cell notation. But on the left-hand electrode, you must see reduction. That's why this acidified manganese 7 was reduced to manganese 2. And since we didn't have any solid electrode this side, that's why we added platinum on this side. Now here you can introduce water or you can leave it out. The difference between the first equation or the first notation and the second one is presence of water. A student who has included water and that one who has not included water are all going to be marked. So you should understand that. Though water we don't normally consider it because we assume that it's present in excess or its presence does not affect our experimental values. So going to number 4, we are given that the convention or the cell notations of the cells are as follows. So here this is your anode and then this is your cathode. Now here you are being told to write the equation of the anode. You well know that the anode is the left-hand electrode. So that means that your equation is going to come from here. You must show that at the anode we have oxidation. Iron 2 ions convert into iron 3. At the cathode you have reduction. So you must show how this acidified manganese 7 is going to be reduced to manganese 2, which is the equation we just displayed here. Then later, we combine the two equations by eliminating electrons to get this overall cell reaction equation. So as that, after following the steps appropriately, you're going to end up with these conclusions. If at all you have really understood what I've said, and if you have not understood, make sure that you reverse and you go back and you see the actual procedures. Now with that, after identifying how to write equations on the anode and the cathode together with the overall equation, now let's go to calculation of standard EMF of the cell. So EMF of the cell is going to be denoted by this symbol and is going to be given by the following. To get EMF of the cell, we get the EMF on the right-hand electrode minus the EMF on the left-hand electrode. But all these ones must be reduction potentials. You must underline this properly. For you to do out any calculation, you must first make sure that you are having reduction potentials. That's the key thing. But here you also realize that your right-hand electrode is always the cathode and your left-hand electrode is the anode. So one can change. Instead of writing RHA, you say E at the cathode minus E at the anode. That's what you should always put in your mind. But I've told you before you do any calculation, the values that you must use must be values, the EMF values must be values of reduction potentials. We are very strict under that. The moment you forget that, you are going to lose all the marks under these calculations. The first thing to do is to identify whether the equations given are reduction potentials. That's the first step. So proceed, we are going to say that if the calculated value of the EMF is going to be positive, the reaction is feasible or spontaneous. But if at all it's negative, the reaction is not feasible. So you should know that. If at all the EMF you have calculated, the reaction is positive, the reaction is going to be feasible or spontaneous. But if at all it's negative, the reaction is not going to be feasible or it's not going to be spontaneous. Now let's look at the examples under that. So with that, let's look at the following questions. So if you look at the following questions, if you look here, all the equations you're having are in terms of reduction potential, simply because you are saying that the oxidation states are changing. The oxidation states are proceeding with a decrease, or the two half equations are proceeding with a decrease in the oxidation states. So that means that these values here are in terms of reduction potentials. So the first value is going to be we'll look at the least value, which is going to be your left-hand electrode. So your left-hand electrode is going to be this one because it has the least value. And then automatically this one is going to be your right-hand electrode. And we said that the right-hand electrode is the same as the cathode, but the left-hand electrode is the same as the anode. So after noticing that, we come here, like we have already talked about this. So I'm skipping that, but I'm interested in the calculation of the overall cell EMF. So we used an equation that EMF of the cell is calculated as E on the right-hand electrode minus E on the left-hand electrode. But for you to realize your right-hand electrode and your left-hand electrode, you must first have reduction potentials. So since we have already identified them, we just make substitutions. But when you're making substitutions, make sure that each and every EMF has its value or has its sign attached to it. don't assume that you are writing 0.55 the same as positive 0.54. We need to see this sign present. Then later you're going to end up with an EMF of the cell which is 0.22 volts. Now since the EMF is positive, that means that this reaction is spontaneous, or the reaction is feasible. And that's the general comment that you'll be making when required. If at all you get a positive EMF, if it was negative, the reaction would have been unfeasible, or it would have been non-spontaneous. Now let's look at the next example. Now with this example, you are saying that the first one is going to be a reduction equation. That means that this one is okay. And then the second one is also a reduction equation. That means that it's also okay. So identify your left-hand electrode and your right-hand electrode. The left-hand electrode has a least value. That means that here, this one is going to be our left-hand electrode, and the first one is going to be our right-hand electrode, or the cathode. So this is your right-hand electrode, and this is going to be a left-hand electrode. Now after realizing that, when you come to part B, because I've already talked about all this, so when you come to part B to calculate for the EMF of the cell, you just hit EMF on the right-hand electrode minus EMF on the left-hand electrode. And our right-hand electrode, we identified it as 0.77 minus EMF of the left-hand electrode, which is 0.14. And you got a positive value. Since it's positive, the reaction is feasible, is not feasible. Because the EMF of the cell, the reaction is feasible because the EMF of the cell is positive. If it's negative, the reaction is not feasible. Just a quick review on this. I said that at the cathode we have reduction equations, and at the anode I want oxidation equations. To get the overall reaction, we add the two equations by eliminating electrons. That's how you end up with this overall reaction. Writing the sign notation, this side on the left-hand side, or the left-hand electrode, I must see reduction taking place, which is written well here. And this side I must see oxidation. No, this side is the anode, so I must see oxidation this side, and this side I must see reduction. If at all you don't have any solid electrode, that's when you add platinum electrodes on both sides. If at all either way you don't have any solid electrode present. So with this is going to be your assessment. You look through these equations, and you try to figure out how this equation, or the answering, or the approach came about. So as your assignment, you try to pause the video and try to figure it out. If you have understood, make sure that you let me know in the comment section. Or if you're having any error, unelaborated. For those ones having any inquiries or any serious issues about specific areas, you make sure that you use the WhatsApp platform in communicating your ideas. So with that being covered, you're going to proceed to the next topic, or next subtopic, that is going to include the calculation of Gibbs free energy. Now Gibbs free energy is simply calculated by negative number of moles times Faraday's constant together with multiplication of the EMF of the cell. So here the interpretation is going to be the number of electrons that are taking part in the process, the ones that you use overall, and then for F is going to be the Faraday's constant, which is already 96,500. We looked at this in the first video. Then this one is going to be called the EMF of the cell that you have just calculated. Now here, the value of N is going to simply be the number of electrons that are going to be involved in writing the overall reaction. Now notice that here, the N is going to refer to those electrons that you get that are the highest. Before you eliminating electrons, you are going to multiply a certain digit by, you are going to first make sure that the electrons are equal. So once you, for example, if after multiplication you have 6 electrons in this equation and 6 electrons in another equation, that means that the value of N is going to be equal to 6. N is going to be the number of electrons that you are going to be using to eliminate each other. That must be equal in both of the equations. If at all initially you're having one equation having 2 and the other equation having 3, and you need to eliminate these electrons in your overall reaction, you multiply this up one by 3 and this down one by 2. That means that the overall equations that you're going to be using are going to be 6 in each equation. So N is going to be equal to those 6 electrons. I hope that is clear. The number of electrons that you're going to be used, that are going to be involved in your overall reaction. So if the calculated value of Gibbs free energy is negative, the reaction is going to be feasible. But if the calculated value of Gibbs energy, free energy, is positive, then the reaction is not going to be feasible. Now we are going to say that Gibbs free energy is also a measure of maximum or useful work that is going to be done by the cell. Now let's open to the examples. Now with examples, since all the above things have been explained, we are just going to go under a detailed explanation of only the part you want. So part A, you can do it, Roman number 1, Roman number 2, you can do it, you can get the overall equation. But however, notice that here, what I was explaining, I'm going to explain the value of n we are using, why I'm using here 10. In these two equations, you are seeing that you are having here 2 electrons and you're having here 5 electrons. The n is going to refer to the overall equations, the number of electrons involved in the overall equation. Now, before you eliminating these electrons, you had to multiply this first equation by 2, also the second equation by 5. That means that the overall equations that you are going to have to be having in either of the equations are going to be 10 electrons and here 10 electrons. Those are the equations we want. We don't want equations from either one. We want the ones that are going to be equal in both of the equations. So that's why we are using our n as 10 in the formula of Gibbs free energy. Now Faraday's constant is always remains the same, unchanged, which is 96,500, multiplied by the EMF of the cell that you have calculated, which is negative 0.84. Now, since here you're going to get your answer in joules, since Gibbs free energy or energy is measured in joules. To convert it to kilojoules, we divide through by 1,000. That's why you end up with that value. But make sure that the sign of the energy is indicated. Now, since the EMF of the cell is negative and the value of the Gibbs free energy gives a positive value, then the reaction is not spontaneous. It's as simple as that. That's the simple and brief conclusion you can make about that. And that's how we deduct. Now the opposite is true. Make sure that you dive into other examples under the UNAIL question banks. I think I gave only one number under this. Now with this, we're going to look at the applications that are going to be involved in electrode potentials. So electrode potentials, we can apply them in predicting the feasibility of a reaction, just like you have seen in the commenting. We can also use them in the calculation of the EMF of the different electrochemical cells. We can also use them in determining the equilibrium constants of the different experiments carried out in the laboratories. We can also use them to determine solubilities of sparingly soluble salts. Now this brings us to the end of electrochemistry. Your advice is subscribe the channel, like the video and share the video to your friends. Now make sure that the colleagues of yours who join Senior 5 on the new curriculum, all this work is going to, and especially under physical chemistry, is going to be appropriate for their coverage. So they should make sure that they consider the same revision tactics or the same revision work or the same revision videos when they are doing their research. Physical chemistry remained almost the same and try to guide you them so that they can have access to this channel. So meet in the next video if at all God allows.